So Bertrand Russell, in his Foundations of Geometry, he has in a way tried to. In the last lecture, I tried to see how Bertrand Russell tried to see geometry vis-a-vis the Kantian understanding of space in terms of priori and a priori notions of whether geometry and the idea of notion of space, whether they intersect or they fundamentally differ. So the developments in non-Euclidean geometry with the discovery of results by Gauss, Riemann, Klein, Beltrami, and many others somehow challenged some sacred notions which we held in the some geometrical notions, which somehow intersected with how we try to define space and how we try to relate the notions of geometry with regard to space, and which gave geometrical truths a sort of foundations which was independent from that of the way we try to perceive the other branches of mathematics or mathematics itself, which led to some divergences when people wanted, if geometries are free constructions of human mind, or they are not given a priori as God given notions which exist whether we want or not, or they are intuitive in their understanding, which are independent of experience, contradicting the human way of looking at things also. So somehow, if they are free constructions of uh, human mind, so what is their larger relationship with the mathematics and logic? So maybe Russell in his earlier stage also being influenced by Frege, who had a project of logicizing arithmetic, and also influenced by Leibniz. So he wanted to look geometrical truths through those very lenses, and in the process he came in contradiction with some aspects of Kantian understanding of space, as well as maybe some the notions. So in that process, he has very much in a nice way he has summarized the all the different geometers, the discourse or the dialogue, which different mathematicians were having. So in the process, maybe the heavy and because the physics of the times was also considered Euclidean, and Euclidean geometry was very well placed in the Kantian paradigm of space and time. So it was very tough to displace the very notions held by maybe a large range of physicists or mathematicians or philosophers in that milieu. So even in critiquing or contradicting, it was just not less than a revolution, not less than a revolution as compared to the revolution of general theory of relativity. Because the revolution of general theory of relativity is of the revolution of going from Euclidean, non-Euclidean, and its relation to whether geometrical truths are intuitive, a priori, or posteriori, or they are analytic, they are synthetic and empirical. So these debates, the Kantian versus the rest of the geometrians, the divergences from them, a new point of view. So it was nothing less than that of a revolution, although it was not celebrated as that of a revolution of general theory of relativity. But the debate, the revolution of going from that geometrical truths or a priori, they are not a priori. They are as much as valid constructions, as much as free constructions of human mind, and they can respond to our different needs of how we explain the empirical world. So here comes the view of Riemann. Maybe once we just depart from Euclidean geometry to non-Euclidean geometry, so what are the motivations of going there? Are the motivations purely logical, mathematical, philosophical, or maybe empirical or scientific? So I'll just see it. We'll start with Riemann. For example, Riemann, what he says, what Riemann, if I'll quote him, the aim of Riemann's dissertation was to define space as a species of a manifold, that as a particular kind of collection of magnitudes, axioms common to Euclid and metageometry, means foundations of geometry. The only axioms seriously discussed by Riemann are not the results of measurement, nor of any concept of magnitude, but are conditions to be fulfilled before measurement becomes possible. So that's important point. So Riemann would want to have a construction of certain geometry or geometries before you are going to apply, or if you are going to relate them to some aspects of the physical world. So the constructions are a priori, and they are as much as valid, and that gives us freedom to also relate them to the constructions of the empirical world. So in a sense, Riemann was naturalists as well as so I just come so this is one part of it. So the second class, only those which express the difference between Euclidean and non-Euclidean species, can be deduced as results of measurements or of conceptions of magnitude, which space is distinction had from other known manifolds. So maybe Riemann, Russell heavily relied on the writings of Riemann and Helmholtz in writing his thesis. So in his thesis, there is the basic inputs, apart from Herbert, Lorentz, and many other people. And there is also a good section he has devoted in principle of mathematics on geometry. So how he describes geometry with the larger mathematics and the larger project of logicizing mathematics as a grand project, which was also in some sense maybe Hilbert also was interested in axiomatizing geometry, Piano, many other people. So maybe Russell also was in that, he falls in line with that very thing. So, but where does he place the writings of Riemann or Helmholtz? So the contribution of maybe Riemann is very much significant in the sense that although other mathematicians and philosophers did mathematically try to prove, or they did show that the non-Euclidean geometry, apart from Euclidean geometry, the deviations of fifth postulate are in principle possible, and they made actual visualization, the constructions possible, whether it was Lobachevsky, whether it was Bolyai, whether it was Gauss. But the role of Riemann is significant in the sense he was able to connect the non-Euclidean constructions of the world of these geometries with regard to the problems in physics and problems in physics. That's it. So actually his motivations was basically to initially to have a relation of analysis and geometry, or making geometry part of analysis, that part of it. But the thing is which differs him from other mathematicians was that he somehow in a significant way tried to show that the non-Euclidean geometry or had something to do with the physical aspect of the world. So which in his larger thing, which he calls as his field theory. So before our understanding of unified field theory, whether they are string theories or any other theories or Wheel's attempt to, or Kaluza, Klein, or Einstein's attempts to have a unified field theory. Maybe Riemann was the attempts of Riemann are precursor to all these attempts of looking physics, geometry, mathematics, physics and geometry and problems of physics in a unified way and constructing a philosophy thereof. So what I would rather say, if to quote him, for example, not only this thing. So our identification, for example, we say that in our naive, for example, we say that today's mathematics, for example, and physics may be said to depend upon naive identification of so-called intuitive space with R3 and with physical space. The sort of thing done in school and lectures for maybe, so we normally talk of R3 space, or space is three-dimensional. So it was very, it was not, in a sense, I would rather say the space, the so much, the prejudice of, I would rather say maybe yesterday's prejudice, yesterday's heresy becomes today's prejudice. Maybe the notion that the space is three-dimensional. So till in the 19th century, Euclidean space was considered, it is the natural space. So R3 was basically, we thought also space like that, rather than it's as a construction. So that identification, naive identification of Euclidean space, so how we can depart from it. So what also the another contribution of maybe Riemann was also, so rather than going from space is having 3 Rn, so you can go for Rn. So as many as dimensions we can think. So the important question is, why, if did Riemann thought of going from taking a generalization of three-dimensional space to the n-dimensional space, or taking three-dimensional space as a subset of the infinite dimensional space of n dimensions? So it was nothing not less than a revolution. Maybe Riemann, maybe, and many other people also thought, maybe Helmholtz. Maybe Helmholtz, being a physiologist also, he had arrived at these. Maybe Helmholtz was maybe later to Riemann. So so he came to his arguments, maybe apart from rigors of mathematics, from the side of physiology. And also people like Bertrand. So how we can construct not only Euclidean space, non-Euclidean space, hyperbolic space, elliptic spaces, positively curved spaces, negatively curved spaces, spaces with zero curvature, which will normally construe as a, which is in a limiting sense constructs, is our understanding of Euclidean space. So our very relation of Euclidean space and non-Euclidean space and mapping them. So that's very also interesting thing, maybe, which at the end I'll try to connect it, how we try to visualize Euclidean space and how we try to visualize non-Euclidean space. And so what do we even mean by visualizing in a spatial sense, and trying and conceptualizing in the mathematical sense? Do these two things somehow, what I should say, dissolve? The distinctions, can it be dissolved? That spatial intuition and a spatial intuition of three-dimensional space and the constructions thereof, are they same as that of logical deductions or logical generalizations from a certain formal axiomatic structure? These two intuitions coincide, or there is needs some nuance, or there are some divergences also. So one thing is, maybe the thing is that maybe Einstein thought of, he came to conclusion of general theory of relativity by learning maybe through Grossman about Riemannian understanding of tensor calculus, and just applying it in a certain. So the thing the problem of Einstein was a physical. He was particularly interested in explaining a certain physical phenomena, and it so happened that he found a ready-made structure which was there available, and it was useful there, and it somehow helped it, and somehow, and that very. But the thing was, the maybe Riemann in a sense was more his very approach of trying to see things in a unified way, and his understanding that the geometries, Euclidean or non-Euclidean, they are, so you can have a unified understanding of things with the of these different geometries with the problems of physics also. Maybe for example, when he said, for example, he had maybe some problems in fluid dynamics. For example, Riemann considered deformations of hypothetical liquid substances in three-dimensional Euclidean space. So this led him to the quadratical differential, from whose coefficients depend on the three space coordinate as well as time. So and maybe people like, it was Einstein who first fully perceived the connection between geometry and gravitation, and it was he and many of his successors who, after Wheel and T. Kaluza, tried like Riemann to include electromagnetism and other fields well. Gauss's agitation at the profundity of length of the Riemann was due to Riemann's modification of Euclidean geometry. It is also possible that Gauss recognized physical significance of Riemann's ideas. So it's an interesting history how things have. So in our extrapolation to mathematics and geometry, from geometry to physics, and then physics, different branches of physics and astronomy. So the connection is very interesting. They are interesting connections, and we mathematicians have them. But one important question maybe is that I'm also trying to grapple, is that before I'm going to say, so rather I'll just quote for it. So rather, as in his own use of plane of Riemannian surface in the theory of functions, he wanted to develop and use his geometric ideas, which I was talking on, and dimensional manifold as an aid to the analysis of algebra and physics. Indeed, by introducing the concept of manifold, Riemann went far beyond the intellectual scheme of both Euclidean and non-Euclidean geometry. So this is, I am just paraphrasing, for example. So in the same way, he talked of something called n-fold extended manifold. So in modern day sense of topology, what we can say, so Riemann introduced what we call today topological space, with the additional property that each point has a neighborhood homeomorphic to the region R to the power n for a given n. He called it as n-fold extended magnitude, and observed that what was involved was discrete manifolds occur frequently, but on the other hand, there are in everyday life such infrequent occasions form concepts whose modes of determination from a continuous manifold, that of positions of objects of sense and colors, are probably the only simple concepts whose modes of determination form a multiply extended manifold. So the notion maybe here, there is another important point when we talk of space. So normally mathematicians, when we talk of the mathematical point, for example, in the Euclidean sense, that when we talk of point, it is something, or line, it's a breadthless, length is a line, or surface is a, or point is which has no dimension. So we sometimes in Euclidean geometry divorce the element of adjectivity with regard to the particular thing. So here maybe he has maybe also talked of the qualification and the quantification of things in the Euclidean geometry. So can we have qualify also some things with regard to the quantities we are maybe measuring or addressing in that sense. So But one thing I was basically also interesting in that, if the question is that our constructions of maybe Euclidean or non-Euclidean geometries, so how does it our and they are maybe uniquely, for example, perihelion of Mercury or many results of general theory of relativity. So you start if the Newtonian gravitational law is uniquely how we can explain things in the Euclidean geometry, and the Riemannian geometry or non-Euclidean geometry is the ideal frame of the general relativity. Does it uniquely say something about the geometry itself, or is the space we are observing, is general relativity the frame is a non-Euclidean? Does it say something more about Euclidean geometry or non-Euclidean geometry, or nature of the space itself, or the geometry, or it's they are mere conventions? So if there can be, so why should non-Euclidean geometry be the ideal? Why should it uniquely explain the phenomena when used in Einsteinian frame, when coupled with the Einsteinian observations of the combination of inertial mass and gravitational mass, and there are those very things? How should it? Why should it uniquely address certain physical things which cannot be addressed in the Euclidean geometry? Does it say something important about the geometry itself, that that geometry is truer or as compared to this thing? Or maybe there are some observations where Euclidean geometry is more useful in formulating things, or maybe geometries are, so it's a very also very sub, you can discuss as many sub geometries, so it becomes a free thing. So there is no intrinsic truth value to a particular geometry. There can be as many geometries, as many consistent, self-consistent constructions as possible, and they can uniquely map to the empirical phenomena which we want to import them into the structure of the logical generalizations they are having. So here I'll rather want to digress a bit, basically in the different schools of thought of mathematics, whether intuitive school, formal school, logical school. Maybe there's also that one school of thought, maybe which there's a famous statement of Hertz, that when he said after the discovery of Maxwell's equations, that equations give more than what you import into them. So equations are more intelligent than the person who is using them. So they give more what. So belief, the belief in the formal structures, whether they are geometrical structures, whether they are self-consistent structures of Euclidean or non-Euclidean geometry, so they have an intelligence of their own, and they may uniquely say something about our physical world to which we map them, or to which we relate them in some physical empirical sense. So this is one opinion. Or the other opinion can be that you can say that they are, so in our current day understanding of multiverses and many solutions, so you can have as many geometries, as many self-consistent geometries, and as many phenomena, empirical phenomena and universes which will explain them. So that, but also somehow, so but there's also another question of how are the geometries when we go from one geometry to the another geometries. So which I have, so truths or statements in one geometries, how can we relate them in the another geometries? So there comes very important notions how we define congruence in Euclidean geometry and congruence in non-Euclidean geometry, or any other geometry which we can construct of, and the deviations or relations, whatever that may be, or overlaps also. For example, when we talk of curvatures, so things when we have positive curvature, negative curvature, And zero curvature, maybe zero curvature sometimes in a, when we just it can explain the results are as if they are the results of the Euclidean geometry in a limiting case. And for example, if you see, if you read Einstein's meaning of relativity, where he just famously has said, for example, he says that, so Einstein found that general in the principle, the most general, that is simplest generalization of straight line in the Riemannian geometry is the straight line is the straight line that is geodesic. Therefore, in accordance with the principle of equivalence, we must assume that the motion of material bodies under the sole influence of inertia and gravitation must be given by that equation, famous equation d2x, where we have that affine connection, where all components vanish. This reduces to the equation of the straight line. So, and maybe when we also, for example, in physics, when we talk of, for example, Hermann Weyl had his books Space, Time and Matter, which Weyl had presented rigorously for the purpose of complex and Riemann's ideas of continuous manifold, and now take part in developing from the very beginning the mathematics of theory of relativity. Weyl came with the idea that one could introduce different gauges of length in different parts of the universe, and metric was therefore determined only to within a variable gauge factor. So maybe beginning in 19 Kaluza followed a different road. He added a fifth dimension to the four-dimensional universe by putting the foundations of product of four dimensions manifold by a circle of small radius, which makes it a periodic function of the fifth coordinate. Only 4 of 5 given nu are needed for the electromagnetic potential. So maybe that how Hermann Weyl introduced the gauge, and the gauge, the choice of potentials has the idea of distance. It might have different gauges, can introduce different parts of the universe, they might have different value. And the developments of Kaluza and Klein, maybe to see electromagnetism and gravitation, maybe the influence of Riemann via Einstein, and whether the introduction of other dimensions and relating them with the different forces, gravitation. So this project has continued since Riemann in a significant way, and in our current understanding of string theory, where unification starts from the basic formalism of the theory. So the project has continued in a very vigorous way, and a lot of researchers have devoted themselves to this grand idea. So how where Russell comes into it, at least Russell has, I have just given more emphasis on Riemann. Maybe Russell has not he has discussed Riemann in a significant way, but not to the point. So maybe I have been biased to Riemann, but there are other people which Russell has talked also, including Lotz, including Helmholtz. There is a famous essay also of Helmholtz on the origin and significance of geometrical actions. Yes, he has given his ideas in a physical way to somehow explain how the reason aditya of non-Euclid construction of non-Euclidean geometries in the background of the Kantian, in the background of somehow negating the Kantian thing, whatever was happening. And I have also, maybe the influence of Herbert on Riemann is also very well discussed. Riemann has heavily taken things from Herbert, the philosopher. So now, before continuing, I will just also say something about, for example, non-Euclidean geometry, and maybe for example, how you can say for problems of physical geometry. So for example, which I was talking, so how when we try to introduce empiricity in the postulates, geometrical postulates, and the so so what is it? So, for example, when you say the geometry of physical case had to be recognized as an empirical problem, it's the task of physics to single out the actual space, that is physical space, among all the possible types of space. It can decide this question only by empirical means. But how to proceed? So this is the question. So how to choose that which geometrical self-consistent geometrical structure is going to describe the world, how to choose even that geometrical structure. So sometimes maybe if the so here it can also be some sort of egg and chicken problem. So if our physical results are our empirical understanding of world, or observational aspects of the world are ahead, so we can just if we can so if the geometrical structure, or so you can see it, so if it's not existing, so you can sometimes our understanding of the empirical world, maybe perihelion of Mercury was not explained by Newtonian mechanics, so this thing came later, geometrical structure came later. But there may be existing geometries or geometrical constructions, so whose map to the aspects of the problems of the empirical world are yet to be discovered or mapped to. So this is one point. So now I'll maybe come to the, for example, question of maybe, for example, so where I feel to one thing I feel to mention is that Helmholtz laid the philosophical foundation, that he recognized the connection of problem of geometry with that of rigid bodies, and interpreted correctly the possibility of visualization of representation of non-Euclidean spaces. So maybe the role of Helmholtz also in clarifying a lot of things has been also significant in the history of relating non-Euclidean geometry with the physical prior to existence of the general theory of relativity, things which made that thing possible. So now I'll come to a very important question of maybe which is very much important in the sense that what do we mean by visualizing things in the Euclidean space and visualizing things in the non-Euclidean space? So, and does it somehow contradict with our the way we try to find the logical consistency with the logical internal self-consistencies, whether that of Euclidean geometry or non-Euclidean geometry? Even though both Euclidean geometry and non-Euclidean geometry are self-consistent geometries, but the fifth postulate, there is something called the existence of independence. Means you can start from starting two or more different starting points, but you can reach to different conclusions. But those different conclusions may come to the same starting point. But whether the starting point, whether the different conclusions, how do they talk to each other? So, or can they communicate, or can there be some relation? So they can draw diverse conclusions. The endpoints may not necessarily, the conclusions of the endpoints may disagree, but their starting points may be. So that's the independence part of it. And the other part of it is that the Euclidean, the notions of spatial intuition, so much was ingrained in this notions of this spatial Euclidean notions of space and or visualization of space, because if you see it, the notions of geometry and notions of space somehow were merged in the Kantian way of looking at things. At least Kant gave a philosophical foundation to why should we think space to be that way. But with the coming of non-Euclidean geometry, somehow it was very tough to say how we can visualize if Euclidean geometries are maybe logically consistent, but there is also special way of looking at visualizing it. The famous statement, they are self-evident truths of Euclidean geometry. How, and we can visualize them in some special sense. But once non-Euclidean geometries came, so going from 3, 4, and more than 4, even Euclidean geometries beyond a certain point, it's also tough to have a spatial intuition in those very problems also. But at least in principle, we could visualize or imagine things in a special way in Euclidean geometries. But once we went to non-Euclidean geometry, so there was one important thing that we could generate if we have a spatial intuition in the, apart from whether they are logically consistent or self-consistent within their own domains. So we could also have a spatial intuition for the non-Euclidean geometries. And how we can imagine, so we can extend the spatial, how we have to basically have the relationship between the Euclidean geometry and non-Euclidean geometry. It can be made very terse, and the way we could visualize the Euclidean geometries, non-Euclidean geometries via Euclidean geometries. And there were the different people, different mathematicians had a different viewpoint on this very thing, whether this exercise of spatial intuition, which was very much potent in the visualization of Euclidean geometries, can be that much useful in the non-Euclidean geometries, or the way in our times when we talk of higher dimensional space or subspace or higher dimensional manifold, the lower dimensional manifolds as a part of higher dimensional manifold, the idea of even spatial intuition, how much it's valid as an exercise, even if we should attempt it or not, or the way algebraic topologists or algebraists, the algebraic rigor of algebra has more value to it than that of spatial intuition, which a lot of mathematicians might have got used to, or whatever you may want to call it. So here maybe I would rather, before I'll come into that very thing here, so how I'll just maybe quote maybe Hilbert. Hilbert has in very much in his foundations of geometry. So he being a formalist axiomatist, so he wanted to axiomatize or formalize geometry in a significant sense. So his opinion was not, so his way of understanding geometry was not he wanted to maybe axiomatize geometry in some formal sense, and the spatial intuition which we have in the geometry, he would not want to take that very thing in a rigorous way. So in that sense, he would maybe for example for example, the Euclidean geometry superimposed upon non-Euclidean plane may be called pseudo-geometry, and new kind of congruence as pseudo-congruence. So investigations by Riemann and Helmholtz of the foundations of geometry led to it to take up the problems of axiomatic treatment of geometry as introductory to the study of groups. So the profound mathematician introduced a system of axioms which he showed by means of his theory of transformation of group to sufficient. Maybe I have also forgot to mention maybe the role of maybe von Klein and Lee in the development of groups, and Hermann Weyl, where he appreciated the notion of symmetry in the idea of geometry, and how we can make the correlations of algebra to it. and how the notions of spatial intuition, how we can visualize the continuous transformations of groups in an algebraic way. So the in the later stages, how the subjects of algebraic geometry, algebraic topology developed in the strict deference to the analytical maybe geometry, where so that those developments are also connected with these very developments. So what I was talking about basically on the Hilbert, when he talks of foundations of geometry, the way he tried to axiomatize or formalize the notions of geometry. So there is a very interesting debate of, for example, uh, uh, of Hilbert with Frege. And why I have introduced this thing notion is that Frege, the way logic, the project of maybe Russell, Whitehead and others maybe was basically to logicize mathematics in axiomatize geometry also. So the debate of Frege, because Russell is the successor of Frege and Leibniz. So the debate of Frege and Hilbert in the visualization of space is very much potent, very much interesting. How they debated with the idea of spatial intuition. So is it as a valid form of reasoning of geometric truths or not? For example. For example, what I say is so geometry when applied to space becomes experimental in character, and we should be looked upon, as Gauss remarked, from some standpoint as mechanics. So this is Gaussian. So recent investigation carefully scrutinized the foundation of geometry led to precise formulation of set of axioms. Following lead of Pasch, Hilbert, Peano, maybe Russell, Whitehead, Veblen have gone in placing geometry, both Euclidean and non-Euclidean geometry, as well as mathematics in general, on the firm logical basis. So it's one conclusion. So maybe what I wanted to say is that basically is that the debate of Frege and Hilbert in constructing geometrical consistency. So how much is the spatial intuition which was very much there in Euclidean geometry? Can we extend that spatial intuition? Should we leave it as of all or not? So Hilbert was of the opinion that the logical consistency or formalization of structures, whether algebraic or maybe geometric structures, will suffice the things. While in case of Frege was not comfortable with these with Hilbert's way of looking at things. So he fundamentally thought that the axioms of, for example, geometry, the spatial intuition which we have from the first principles in the constructs of geometry, they have not to be dispensed with. So in that process, if you read the exchange of letters between Frege and Hilbert, so you could see Frege again and again mentioning that spatial intuition is as much a way of looking at things, where Hilbert is responding by saying that the problem is basically of respond a particular proposition or assertion which we take into consideration has to respond in a prior way to a particular need. So we have to map a particular proposition. So the point was, a given proposition can lead to multiple interpretations, which was problem for Frege. But for Hilbert, so that was the problem that which led, according to the understanding of Frege, to some contradictions. So how Hilbert wanted to circumvent those very foundational problems of geometry and geometry and axiomatization of geometry was that we have to assign a particular proposition, a particular value prior to what we are going to deduce things thereof. So this is one way of his way of. The point I wanted to basically emphasize is that so the logicization of maybe arithmetic for Frege was possible, but for logicization of geometrical axioms in the so Frege had some problem, but Hilbert, Russell, Peano, and many other people, maybe Whitehead, Veblen included, so they extended the same debate in that very sense. And those very debates may have some maybe the debates may still have some of the relevance to the point of trying to the epistemology of what I should say, the truth values of the foundations of mathematics or metageometry also. And maybe these very discussions maybe ultimately maybe you can in some sense connect them in the Godelian sense also, maybe the may not connect them in Godel sense, but I'll say that the program of maybe Godel of arithmeticization of logic, which was he showed them in terms of propositions, is not possible. And one of the conclusions of that was that maybe this is off the track. Maybe I'm not. This is off the track. Off the track. Can connect them in some different way, but so what so for example so I'll just connect them in some significant way. Also, so for example, the truth of my division of axiom of for example of dimensions into a priori and empirical portion, while the extension of the number of dimensions to 4 or to n alters nothing in plane and solid geometry, but only adds a new branch which is interferes in no way with old some definite number of dimensions, is assumed in all geometries. Nor is it possible to conceive of a geometry which should be free from this assumption. If geometry is to be possible, it is a priori necessary that space should have finite integral number of dimensions. So maybe the number of dimensions, whether Euclidean or non-Euclidean dimensions, according to Russell, you should have some dimensions to it. Whether 3, 4, less, whether solid geometry, project. So maybe one thing, important thing in Russell's maybe principles of mathematics, he has discussed very things. How geometrical truths, how we construct metrical geometry, projective geometry, metrical geometry, and how we can map things from this geometry to another geometry also. And how some axioms which are there, for example, the axioms of distance. So for example, one good sentence in Russell's Foundations of maybe Principles of Mathematics or Foundations of Geometry, somewhere he writes that. So we assume that, for example, axiom of mobility. So even in Riemannian geometry or Helmholtzian geometry, so we have some axioms. The way we have axioms of Euclidean geometry. So those axioms is one of them is axiom of mobility. So if you have from point A to point B, so you want to translate that space to some another space, that space will not change. So if you want to move, for example, a book from point of length AB, we assume that its length will not be changed when it moves from B to C, where AB is equal to BC. We cannot say its length is not changed. So this is an prior assumption of geometry. So for example, if in our practical sense, for how we can see it is that if we have two books, one is red book, one is white book, if they have if are of the same dimensions, if I will just displace one with the another, we can say the movement has taken place. But if they are of the same color, the same magnitude, we will not be able to differentiate that very action. So it's a very this axiom of mobility means we just assume prior to that space has some character. So the nature of space will not change when we introduce some motions or distortions or whatever that is. And maybe there is also these notions of maybe space is finite or infinite. So these things, so these notions of axioms of mobility in metrical space or Riemann, so those very axioms, if they are not held according to Russell in a serious from first principles, so they will lead to contradictions. They will lead to so geometry is not will not be possible, Euclidean or non-Euclidean, whatever you might want to say. So I want to say something more, maybe. So I'll just maybe there is to add to the discussion, maybe which is not entirely relevant to Russell. Maybe there is a famous in the discovery of non-Euclidean geometry. Bolai has is a very out of nothing I have created strange new universe. So maybe he might the discovery of non-Euclidean geometry, even though it was discovered in medieval times also by people like Nasir Tusi, I would say rather rediscovery of non-Euclidean geometry had a significant it's the history is very much interesting, and maybe this statement can be read in that very context. Out of nothing I have created and strange new universes. And maybe I would, or we can even our understanding of maybe in 20th century, our really new understanding of multiverses, or in swampland, or maybe solutions of the universes which we have. So maybe this is a hunch, or this is a general loose statement, maybe whether the self-consistencies of the geometries which we are having, and maybe geometries are a free construction. The only imposition is that we in geometries we say that the constructions are self-consistent constructions. So self-consistent constructions which we impose on geometries, and those self-consistent geometries can be as much possible as we can construct them. So what has it to do with the sort of multiverses or multi-universes which we are constructing, or which we are even theoretically constructing as solutions of the different branches of string theory or many world view of universe? So maybe there can be at least loose conceptual you can say, you can relate them. So that it might in some sense loosely maybe militate against, maybe I'll come to the religious part of it, debate somehow our that the world is out there to be discovered. Maybe the famous statement of Albert Einstein, that the most incomprehensible thing about the universe is that it is comprehensible. So this means that when you talk of that universe is comprehensible, means that our rationality, or there, we presume there is a world and that world is objective, and we are in that perpetuity trying to discover, and that it slowly and gradually you are trying to come closer to God, or we are becoming gods, or we are trying to uh, the famous statement of Kant as well as Helmholtz, that there is a pre-established harmony in the prior constructions of the space and what we are going to discover. So this is a pre-established harmony. But if the conclusions of non-Euclidean geometry, so if there is a freedom to the constructions of non-Euclidean geometry in a certain in a broad way. Maybe Einstein tried to, maybe he had a physical problem of wanting to explain a certain physical phenomena. So he tried to restrict the Riemannian construction of particular construction of space. He narrowed it down in a certain way, and he could explain the real physical aspects of a world. But in principle, you can have those constructions can be. I will not say they can be vague, so there can be a lot of freedom to those constructions, but rigidity is that those should be internally self-consistent. So if there are as many geometries we can construct, so there can be as many universes in which those geometries can be mapped to. So maybe this maybe discussion is off the hand, maybe big, or whatever you might want to maybe input it to whatever I have said. So what I had, so I'm going to now just conclude of so how maybe the maybe before I'm going to conclude, maybe I have not given the enough contribution. Russell, in his foundation of geometry, he has given enough. He's also praising the lectures of Klein on non-Euclidean geometry, which he has had. So there's also contribution of Klein also in this very debate. Maybe somewhere he has written, there's another person called Lutz. So he was a Kantian, but he somehow, maybe Klein suffered because of his views. He wanted to critique Kant in a significant way. So that's off the comment. So maybe I've missed, maybe lost of points. But what I would rather say is that maybe the role of Russell in trying to formulate a significant debate in the earlier part of 20th century of how the geometry, the role of how the role of geometry. So in this thesis, he is not interested in logicizing geometry or axiomatizing geometry in a very overt sense, which he has taken in his principles of mathematics. He has, if you read principles of mathematics, so you could see that maybe the portions of geometry he might want to connect it with the rest of the book. But in this essay of foundations of geometry, he has more or less tried to summarize. He has tried to summarize the various debates or various contributions, mainly that of Riemann, Helmholtz, Lorentz, and many other people, Herbert, in connection with the geometry, and in connection with the Euclidean geometry and non-Euclidean geometry. and the empirical aspects of the things, how we construct the empiricity of things with regard to the Euclidean and non-Euclidean geometry, and the opinions of various people. General theory of relativity was yet to be discovered, but maybe that, in a sense, he contributed. That was his contribution. He somehow summarized that dialogue or debate between the Euclidean geometry, non-Euclidean geometry, and Kantian notions of space and time, and how much it was significant, in a sense, to break away from a tradition. Not significant, how much, I would not say it was significant. So how much he has articulated the difficulties, philosophical difficulties, and maybe at some point in he has time he in the book he has come to the conclusion that we have reached a stage from uh, philosophical churning, the metaphysical underpinnings. We have reached a stage that the subject of Euclidean and non. So we have reached to a point where it has become more technical. So we have become we have a formulaic understanding of that's the last stage of the subject, and the role of philosopher or philosophizing is more to their starting point should be start from that very point. That maybe this debate, although Russell also is still one of the link in that very thing, maybe he may not have been that significant contributor, but he might his even to summarize it and to state the different people who are engaged with it, and trying to just give a coherent picture to this debate. So that is significant, at least.